Okay, thank you. So this is joint work with two people in the audience, Jennifer and David Garmanik, sitting there and there. Jeff Kahn and Laci Lovas, which is earlier part of this work. And so what are we interested in? So we have a sequence of graphs with more and more vertices. Okay, think of it as the internet when it started years ago and sort of a few years ago and now, and it's very soon reaching this infinite number of vertices as far as I can tell. And we want to ask ourselves, well, in which sense could we say that graphs, the internet 10 years ago and today are similar to each other? And mathematically, that's a question of convergence, okay? And now, what's the right notion of convergence? This may really depend on your audience, okay? So if you ask an extremal combinatorialist, they will say, well, I want to know how many triangles this has and how many Peterson graphs it has. And they are aware that the number of triangles might go up as the number of vertices go to infinity, so divide by some power of the number of vertices. And then if all these numbers converge, you call it sort of convergent for extremal combinatorics. We call it left convergence for a reason I will come to. You could ask computer scientists and they say, look, these triangles and stuff, I'm not really interested in how many triangles your internet has. But I'm interested in sort of things like max cut or min bisection or flow or whatever things, sort of more global properties of your graph, which leads to a different notion of convergence, which is we'll call convergence of quotients. I will explain all of this. And finally, you may ask your friends, the physicists, sitting, for example, there, behind David, and they will say, this is all not that interesting. I want to know sort of when the free energies converge, or if you have machine learning people, they want to talk about graphical models, and that will lead to note something like right convergence, okay? And a priori, everybody has their own favorite notions. The question is how they're related to each other. So together with Laci and some other co-authors, Vera Schoos and who is that? Westergombi. So myself, Jennifer, Laci Lovas, Vera Schoos, and Kati Westergombi, we introduced these notions of convergence for dense graphs and proved that they're equivalent for dense graphs. And then there's lots of follow-up work. I mean, sort of immediately in the beginning, Laci, together with one of our postdocs, proved that you have a limit object. And then in this talk, so I will want to look at the opposite end. So these were dense graphs. So these are graphs where the degree is proportional to n. And here I will want to look at the case where we have sequences with bounded degree. And I will show to you that all these notions are actually not equivalent anymore. And furthermore, I will introduce a new notion of large deviation convergence, which implies all these other convergences. Okay, so let's start with some notation. So we have two graphs. Think of f as small and g as large. And then we have a map from this small graph into the large graph. And this map is called a homomorphism if edges are mapped into edges. Okay, and then we say that a sequence of graph is left convergent if the probability that a random map from the small graph into the large graph, so you're testing the large graph from the left, that's why it's called left convergent, if this probability that this random map is a homomorphism, if that converges for all simple graphs f, right? So you take a map, and this may or may not map edges into edges, and if it does, you count it, and otherwise you don't, and you look at this probability. That was not what I wanted. Okay. So it's not that hard to show that the following is true. So if you, instead of looking at the probability, you could obviously look at the number of homomorphisms divided by the number of all these maps. The number of all these maps is just the size of the big graph to the size of the small graph. And you could add the number of graphs which are homomorphisms, and then you can relate homomorphisms two isomorphisms via some inclusion-exclusion, and you can see that the two are sort of equivalent. So in other words, what does this say? So now what is this guy? Well, this is a number of subgraphs F which are isomorphic to F. So now we really count how often you, for example, see a triangle in the big graph Gn. Okay? And the homomorphism is just a sometimes more mathematically more convenient way where you count it in many ways and you, anyhow, they're not that different. Okay, so what about quotients? Okay, so that's my second notion. So let's fix some coloring of your graph. So now we do a map from the graph on the left to the right. So this will be later related to right convergence, but you can already think of this testing sort of on the right. So I color this graph vertices with some colors 1 up to q. Okay, and then let vi be the set of, this guy is the set of red vertices, green vertices, and so on. And now what do I look at? I look first of all, how many, what's the percentage of red and green vertices and so on. So that's one kind of information I keep. And the second kind of information I keep, I look how many edges go from red to blue. And how many edges go from green to blue, and so on. And then I normalize by the total number that could be, but it can never be more than 1 over n squared. Okay, so if you have this large graph, now you color it and you keep just this much less information about how many edges go between different colors and how big are the different color classes. Okay, and now for a fixed Q, so a fixed number of colors, now you can vary all possible maps, and then you sort of get some image of what the different sort of number of edges between red and green could be depending how you color red and green. Okay, so this set of all possibilities we call SQ, and it's called the set of Q quotients. Okay, now we define the sequence to be convergent if this set of Q quotients converges in the Hausdorff metric. So let me see whether I give a definition. No, I don't. Okay, so Hausdorff metric. Okay, so this set of quotients is obviously, I have only a finite number of maps for a given. Does this not go back? So I have only a finite number of colorings there because I can only sort of a finite graph and have, well, exponentially many, still only a finite number of possible quotients. So I have this set of quotients. Okay, and I want to say that this set of quotient converges, and as the number of vertices becomes larger, this guy becomes larger and larger. Do we have a different color? We don't. So you expect maybe that converges to some continuous set, right? Let's say there's some hole in the middle. So what does that mean? That sort of a set of discrete points could converge to a continuous set. Well, in the Hausdorff distance, what you say is for every set in this discrete set, you can find a point nearby in the continuous set such that eventually you find one there, and the other way around. So for every point in the continuous set, so for example here, if there's never a point appearing here, I better put a hole here. Okay, so it sort of fills this densely out. And you can even say I have two discrete sets when these 2 points are all for each point. So I have a set of blue points and a set of green points. And for example, these are far in the Hausdorff matrix because this point doesn't have any point nearby. Okay, so each of these blue sets points has one in the other one nearby, but this one doesn't have one near. So this Hausdorff distance is large because the nearest point is this distance. Whereas if you had sort of these guys here also, then the Hausdorff distance. So is it clear what the Hausdorff distance is? Should I write down a formal definition? No. Let me not write down a formal definition. Okay, So you have some intuitive notion what it means that these sets get near. Okay, so why is this good? Well, you can express with these cuts, you can express a lot of interesting with these quotients. So for example, what would be max cut? So I color with 2 colors, okay, and I look how many edges are between red and blue, so 1 and 2, and I want to maximize this over all these possible 2 colorings, right? So then I only need this information. So the max cut is actually just given by that. What if I wanted max bisection or min bisection? Well, if I do min bisection, I again minimize over all possible colorings, which is the same as over these quotients. But now I fix that the weight of one of these guys should be 1/2, which means half the vertices are red and half are blue. So many interesting things in combinatorics I can actually express in or in computer science, whatever you want to call it, I can express using these quotients. So in general, I can express something like, yes, David?
Why do you have a square in the number? Why do you normalize by this?
Because I have dense graphs.
Oh, you dense.
Okay, so I have, in principle, I could have n squared edges between these 2 classes. And for example, I take a random graph with probability 1/2.
We didn't realize you were doing that.
And in general, I could, for example, say, okay, I want you to calculate what would be the minimum of red-blue edges minus 1/4 the blue-green edges plus pi times the number of black-white edges. And you want to maximize it in such a way that red has sort of 1% and blue has 98% and black has sort of half of the rest and white also has half of the rest. And for some reason that is something which you actually in your coloring problem, you have some optimization problem which you're interested in this quantity. Well, then you have to calculate these quotients for whatever my numbers of colors was, 5. And once you have that information, you don't need to know this big graph, you only need this polynomial number of numbers, and you can calculate these quantities. Okay, so that sort of is a nice representation of your graph if you want to calculate generalizations of min and max cut and things like that. So what do statistical physicists want to do, or actually machine learning people? Well, so what we now look at is we have something called a soft-core graph. So this is a graph which is weighted, and you have edge weights, which are some beta ij, which are positive. And now what do we do? So we define a homomorphism. The prime I will explain in a minute. So forget this here at the bottom for the moment. So we just sum over all colorings. And now we put here this soft core weight. So all of these have non-zero weight, but I weigh different combinations of colors differently, right? So maybe I want to highly favor red-blue edges. And this is sort of, it's what machine learning people call a graphical model, where you actually have, you want to sort of, each vertex is sort of in your model is in certain states, and you have some prior probability about correlations between the edges, and then you want to sample from that. And now you want to learn maybe these betas. So this is an object which people are very much interested in machine learning. Maximum likelihood would be corresponding to find the maximum of these guys and things like that. Okay. Now for statistical physicists, this is just what people would call the partition function of some models. So for example, if you have the Ising model, these beta ij's are, let's say, E if I equals j, and e to the -1 if I is different from j, or more general, e to some constant and e to the minus some constant, depending on whether your neighbors have the same color or a different color. And then this thing will want the neighboring colors to be the same, and it describes a magnet where spins want to be aligned. And now here is a prime. What does this prime mean? Well, prime means microcanonical homomorphism numbers. And microcanonical means that I actually want all the color classes to be roughly the same. Now, they can't be exactly the same unless your number of vertices is exactly divisible by q. And if it's not, then we allow it to differ by 1. okay? So we make them as near to each other as possible. That's called the microcanonical ensemble. And the dense sequence is called right convergent if now you take this number, and how large could it be? Well, these could be exponentially many terms because they're exponentially many columns. But the number of edges is actually goes like n squared, so this could grow like some constant to the n squared. So if you take the log, you should divide by n squared. Okay, and if that converges for all possible soft core graphs, so for whether it's on 1, 2, 3, 4, 5, all finite age, finite non-zero weights, then it's called right convergent. Okay, and the main theorem for dense graphs that all these notions which a priori really look very different are actually equivalent. Okay, and the proof uses several ingredients from sort of combinatorics, some of them motivated by statistical physics. It uses the cut metric, which I don't think I will go into. There's some metric introduced by computer scientists at some point. It uses sampling, it uses the famous Samaredi lemma, and so then it establishes that all these notions are equivalent and actually are also equivalent to convergence in this cut metric. I will not go into the proofs here. Okay, so but this talk is about sparse graphs, so this was a little bit background. So now we want to consider sparse graphs, right? Because you will say to me, this is all very nice, but in most networks we see around us, I don't have in the internet, maybe I link to a lot of pages if I'm sort of a spam web page, but even the spam web pages don't link to the 100 billion web pages or whatever we know of currently. I don't know how many are in Russia. Yes?
Just as a quick question, I mean, for somebody who doesn't know much about these metrics, which of these is the easiest to think about? Because, I mean, they all seem...
Which one, which...
Science one is the easiest to think about.
The min cut and max cut and things like that, well, it really depends on your background, which is the easiest, right? I mean, for physicists, a free energy convergent is a very natural question. For combinatorialists, they really want to know how many triangles a graph has, right? And that, right? So you want to know, right? So the density of triangles, the density of 4 cycles. So that's also a very natural one.
Yeah, it seems conceptually very natural.
Right? Min cut, max cut is sort of conceptually easy, but then if I sort of want to generalize, I have to introduce these quotients. They're a little bit sort of not intuitive, but you will get more intuition for them because I will beat you over the head with them again in this second part. Okay, triangles you will, so from now on we want to consider graphs with bounded degrees, which is sort of, in many cases, a better approximation to real life than dense graphs. I mean, maybe the real world lies somewhere in between, but here let's look at bounded degrees.
Bounded degrees or bounded average degrees?
Bounded degree. So you're right that you're right that actually we should do bounded average degree, but it turns out that if you do, and I actually don't think we really have counterexamples. We were sort of lazy. It turns out this was complicated enough to write up for bounded degrees. And there are sort of certain things. We have to do large deviations at some point, and the spaces become non-compact. And it's not that you can't do large deviation on non-compact spaces, but certain equivalences don't hold anymore. And we didn't feel like doing all the epsilons, at least in the first run. So a lot of these things should actually go through for bounded average degree, but we haven't done it. So we have 2 simple graphs, f and g, and again, we denote the number of homomorphisms from one to the other by hom f into g. Okay, so this is the homomorphism number, the number of homomorphisms from f into g. And we say that a sparse sequence is called left convergent if the number of homomorphisms divided by the number of vertices converges for all connected simple graphs. So why do we do this normalization? Think, for example, of a piece of the square grid. okay? Well, you may want to count the number of triangles, that's 0, so that's not hard to normalize. But let's say you want to count the number of force cycles, and then you see that if you have sort of an n by m grid, that's a n by m force cycles. And if you want to count the number of 6 cycles, I don't know, there's this one, and well, or you could go up, and again, it will sort of a constant times n. So for a lot of the sparse graphs, this is sort of a reasonable normalization, and so that's how we define this. Okay, so we say that a sparse sequence is called left convergent if 1 over the number of vertices times this number converges for all connected simple graphs. And it turns out that, again, we can use inclusion-exclusion to write the number of homomorphisms in terms of the number of surjective homomorphisms and the number of so this n of f prime g was how often do you see f prime in the large graph G. And if you do homomorphisms, for example, if I see this guy, right, in here, this force cycle, I could do, when I do homomorphisms, I can sort of have to divide because I could map this, I could call this 1, 2, 3, 4, I could call this 1, 2, 3, 4, or so on. So you have to divide out that symmetry, which is this surjective of f and j. So this is actually, it says surjective, it doesn't say automorphisms. Why? Well, because for homomorphisms also, for example, if I want to map this thing into here, I could, so this is 1, 2, 3, 4. I could say this is 1, this is 2, this is 3, this is 4. That's a homomorphism. And now actually you have to first, right, so you have to map this into 1, 2, 3, 4. And then you look how often do I see this here. And if you work out the combinatorics, you get this formula here. Okay. Yes, that will be exactly. So once you have convinced yourself of this, you see that this is the same as counting how many graphs you have. And now you can sort of say, okay, I divide by n, and then I count how often I see a graph here. So in other words, I can say, let's choose, so dividing by n is the same thing as looking at a random vertex. And then you would say, how often do I see this force cycle with this vertex in there? And which is not very different from saying, okay, I start with a vertex and what do I see in a certain neighborhood? With again some, now you have to go from this back to that via a similar argument like this one, inclusion, exclusion. And what you get is that, okay, so this is a different notion. I want to call it Benjamini-Schramm convergence. This is this local weak convergence. So what does that mean? You choose, so we have a large graph and we want to know a sequence of graph is convergent. Okay, let's say the internet. What do? I choose a random vertex in the internet and then I look around me and say, how does my neighborhood look? And since I'm nearsighted, I only see a certain distance, so I have a certain radius up which I see it. And now I want to know, now I go on a random vertex, so I will see a random neighborhood. So depending on n, I have a different probability distribution. If this probability distribution converges, the sequence is called Benjamini-Schramm convergent. So these were, some people introduced that for trees and stuff, Aldous I think before, but Benjamini and Schramm really introduced this general notion to define what is this kind of convergence. So for every R, you want that the distribution of the random R neighborhood where you choose the root randomly in your graph converges. And answering Remco's question, left convergence is equivalent to Benjamini-Schramm convergence. For bounded degree. For bounded average degree, that's not true. However, it's true if you formulate it correctly. The problem is that, well, you have to actually do what Jennifer did. You shouldn't count just homomorphisms. You should count homomorphisms and you have to know what the degree here is. Because otherwise you might have much too many Well, I can explain. You look confused. It turns out that for bounded average degree, you have to modify the definitions, otherwise it's not true. And every statement I will say to you from here on, I will have to make remarks which make you look funny. And since we didn't want to deal with that with the referees, we decided to choose bounded degrees. No, we were just lazy, anyhow. Or maybe we didn't know whether it would work, anyhow. So we can therefore now, since we have this notion, we actually have a notion of the limit. Because the limit of this Benjamini-Schramm sequence is just a random rooted graph, right? Because we say this probability distribution has a limit for every r. They are sort of obviously consistent. If I look at r plus 1 and I integrate out the outer thing, I get back the distribution. So you have a notion of an infinite rooted random graph. And the limit of this left converging thing is an infinite rooted random graph. So example. Okay, so if we look at these boxes here, n by n, let's say, or if I look at the torus, they both converge to the same rendered random graph because I look at the origin. If I look at a finite horizon, I don't see that the boundary is a torus or not. And I will see just this root, which is 0. And why do I have difficulties with that? This 0 root, and then I see sort of this infinite thing. Another example, let's take a deregular random graph. Okay, so or I can take a deregular bipartite random graph. And if you know a little bit about these random graphs, they both look like trees, because it turns out that you have to go up to distance log n before you start to see cycles. So they actually locally look very same. And so both of them actually converge to an infinite deregular tree. Now this might start to worry you, okay, because you say, for example, if you're a computer scientist, you know, well, one is bipartite, one is not. They're very different, right? For example, if you try to color them, you will have problems with one and not with the other. So you may so there are two remarks, right? So this notion of left convergence is a very local notion. And the second point, the example raises sort of the question whether maybe the topology is sort of too coarse, because it doesn't distinguish graphs which you are saying to me are clearly different. So what do we do about that? Well, one thing we could do, we could again look at these quotients, okay? So again, I'll introduce the quotient. So let me repeat what this is. I look at the coloring. I look for each given coloring. I look at the percentage of vertices which are red, green, blue. And then I look at the number of edges which are red, blue, red, green, and green, blue. I count all of them. But now, since we have bounded degree, if I divide it by n squared, this would go to 0. So now I only divide by n. And the set of these quotients I again denote by SQ. And we say that the quotients converge if these sets converge in the Hausdorff distance in this sense here. Okay? Now, again, you can express things like max cut and min bisection and so in terms of these things. So one thing you might now ask, does left convergence imply convergence of these quotients? Well, probably not, because I already indicated that it's a stronger notion, but let's see that this is actually not the case. So let's Gn be the deregular random graph for odd n and the bipartite regular random graph for even n. Okay? Now, it's well known that for large d, so you can calculate the max cut in this bipartite guy very simple. It's sort of the max cut you cut in the middle, and half the edges get sort of, the degree times n half is the number of edges you get from one side to the other. Exactly. And if you do max cut, well, it's not bipartite. If you look at it, you sort of, if you look in average, only sort of half the edges you would think will be cut, so you get a half here. Just this you can get easily by looking at expectation. And so as a consequence, so these are very different numbers, okay? So what does that mean? Well, these max cuts are very different. So this means that these guys, the quotients are not convergent, because if I sort of know that, right, I have a set here, I have my quotient set, and now I calculate sort of the maximum of beta 1, 2, so I sort of calculate, so I do sort of something like that, and for one of the sets it converges to something, and for the other set it converges to double that much. Well, that means clearly that these sets, and there's a point here which is a large distance from that point, so they can't converge in this Hausdorff metric. So in other words, but I already told you that both of them converge to the infinite deregular tree, so left convergence does not imply convergence of quotients. Okay, so maybe the other way around. Quotients implies left convergence. Well, it turns out that's not the case either. So there's a counterexample. You take, for even n, you take a union of 4 cycles. And for odd n, you take, well, the other way around. For even, well, it doesn't matter. And for the other one, you take a union of 6 cycles, okay? Now, clearly, they don't look the same in terms of left convergence. You can see whether I have a 4 cycle or 6 cycle by looking at distance 3, right? Because in one case, you sort of have nothing anymore, and in the other, you sort of, so on the other hand, if you calculate the max cut, you will see that this is actually just 1/2, right? Because each of these cycles, you essentially sort of, since these are all bipartite, you know how to cut the maximum number of edges. The max bisection is also this number. And actually, more general, you can show that these Q quotients are convergent. Okay, I will not prove it formally for you, but anything you might think of testing there, you can immediately see, and I can actually prove it to you. So in other words, here we have something which is now the opposite. You have convergence of the quotients, but not left convergence. So that neither implies each other, okay? So let's go to right convergence, the stuff statistical physicists are interested in. So again, I have a weighted graph, which you should think of describing some statistical physics model. These weights say how likely the spin, the neighboring spin sort of, this is color red and blue, how likely it is that red and blue are next to each other. If beta is larger, it's more likely. And this is actually, you sort of have a priori, you can sort of say, I want more red or more blue, so you put different weights here. And then you define this number here, the number of weighted homomorphisms. So now you color the vertices of G with the color in H. And rather than looking whether this is a homomorphism, so if it were homomorphism, you would put here the adjacency matrix and put 0 if edges are not mapped into edges. But now you just put different weights depending on what color the 2 endpoints have. And so this physicist will call a partition function. And physicists will look at something like the log of this guy. Now, why do I divide by now the number of vertices? So there are exponentially many ways to color. And now the number of edges, since the degree is constant, the number of edges is also, maybe it's 2n or 20n or whatever. So this grows exponentially in n. The number here grows exponentially in n. This grows or falls exponentially in n. So if I take the log and divide by n, then clearly I get at least something which is bounded. And if it's not only bounded, but it's convergent for all soft core H, so for all these weights and all possible numbers of vertices, then we call this guy right convergence. So for the physicists, that just means that all statistical physics models converge. The free energy of any statistical physics model you want to think of, at least as long as it's discrete, converges. Yes, and that's why we call it right. Except that, well, these days, maybe you want to be on the other side. So now, it's not that hard to show that, for example, these objects are actually right convergent. Huh? And you may wonder, does left convergence imply right convergence? And the answer is, again, no. And why is that the case? Well, it's related to our max cut problem here. So let's again choose this guy, which is sort of either the bipartite bipartite random graph or just the random deregular graph. And now let's choose for H, we choose the Ising model. So we choose the weights of, if the color is the same, the weight is 1. If the color is different, we choose it E. Okay, and then what do we have? Well, if you look at this guy, okay, you can, what could be the maximal contribution? Okay, so we had this product over. So you had this product over the edges, and then you had beta, the color at X, and the color at Y. And now, if we choose sort of the, so and this one will be E if they're different, and 1 if they're equal. So how can I make this maximal? Well, I can make it maximal by have as many edges where the color at the two endpoints are different. That's max cut. So you can clearly bound this guy by e to the max cut. And then you have sort of at most 2 to the n terms. So if I sum over all these guys, I have 2 to the n terms. And there is one term at least where I get the max cut, so therefore I have a lower bound of e to the max cut without the 2 to the n. So that's your bound here. And now if we now sort of look at these graphs with large enough d, the max cut is so different that actually even this 2 to the n, it's sort of, I mean, the max cut, the size of the max cut goes up with d, and this max cut is sort of double as large for the bipartite guy as for the non-bipartite guy, so this won't converge, okay? So does right convergence, so what about the other way? Does right convergence imply convergence of quotients? Well, that turns out to not be the case either. How am I doing on time? I have, how much do I have? I have 45 minutes. Okay, so I can, so why don't we, so you might wonder, well, so maybe that's the case. Well, that's not the case either. So let's again look at an example, okay? So we have, let's say you have some sequence of graphs which have min bisection, which is delta times n, okay? So you have this graph which has, no matter how you divide it in two pieces, you always get a lot of edges from right to left. For example, you can choose your random regular graphs. I would do that for you. And now assume that Fn is right convergent. Okay, if it's not, choose the subsequence until it gets right convergent. The subsequence then will still have this bound. Okay, and now choose your sequence to be these guys if n is odd, and choose it the intersection of the union of these guys at half the number of vertices disjoint of each other if it's even. Okay, so what do we have? Well, if you calculate the homomorphism of these guys, okay, for odd, you just get this guy with Fn. For even, you get a disjoint union here, so these homomorphisms just factor into the homomorphism on one part and the other, so you get just the homomorphism of this squared. Okay, so if you take the log, you have a 2 here, but you divide by n halves, that just works out nicely. That actually, so take the log, divide by n, then sort of this n half, and this is all works out nicely, and it's exactly the same, whether you're even and odd. But now look at the following. Now the min bisection is 0, because I took this disjoint union of the two graphs. So this means that for the odd guys, you have really a min bisection which is huge. For the even one, it's 0. And so this means that this guy is right convergent, but the quotients are not convergent because the quotients alternate between a finite number and minus infinity. So what is left? Well, there's one implication we have, which is that for sequences of boundable and maximal degree, right convergence actually implies left convergence. Okay, so I will not do the proof. Well, I may go back to the proof, but before I do that, let me just, so what do we know so far, okay? So left convergence, I said to you, was not, this was sort of, didn't imply convergence of quotient, because we said this was very local, and that is sort of global, and you can't conclude from the convergence of these local properties that these global quotients converge. It turned out, though, however, that from these global quantities, you can't really conclude the local quantities either. We saw that left convergence didn't imply right convergence, which was related to sort of this guy by just looking at the right limit. Right convergence didn't imply convergence of quotients by this example of taking a graph with a sort of relatively large min bisection and then taking this graph and disjoint uniting it with itself. And but right convergence does imply left convergence, and there's one error left. So could this guy imply this? No, it can't, because if this guy implied this, then this guy implied this, and this guy implied this, so this would imply that, which we know it doesn't. So this is the diagram, okay? So there's only one error, which maybe should I show the proof to you? So how would you want to prove that, okay? So we have a simple graph f and some graph h, and now we define a funny quantity, okay? This is the object we are eventually interested in, okay? And now I look at something which some of you may have seen, the Möbius transform, okay? Or let's look at the other way around. Look at this, insert this here, then you see that you'll get inclusion, exclusion. And so the largest term would be here f equals g. If f equals g, then this is empty, so that gives +1, and you get again logged, so you get the same term, so you actually get that term. And now the next term has a minus sign, but then there are sort of more and more terms, and they all cancel each other out. And if you have ever done any inclusion, exclusion, you sort of will see that immediately. Okay, so we have written, therefore we have now written this log hom as just a sum over subgraphs of this quantity, okay? Now, it turned out that if you look a little bit, this homomorphism I already told you before, if we decompose this G into two connected components, it gives sort of the product of these. So then if you take the log, you get the sum. And then actually, if you look at these minus signs, you will see that actually this guy is just 0 if your graph f is not connected. Okay, that's sort of an easy, it's an easy calculation. And so what does this give? So now we have that this log hom can be written as a sum over f subset g, where f now is connected. Okay, and now what is this here? Well, I have to now, here f may appear many versions of f subgraphs were here, right? But a lot of these subgraphs, there could be little guys like a fourth cycle. It could appear many times in G. So here we just count how often it appears, and then obviously now we only sum over isomorphism classes. Okay, now why is this interesting? So G is large, okay? Now if this sum would be convergent, okay, then what would we have here? We would have these numbers n, which you remember are related to left convergence, because that counts how often do you find f in the large graph G. And this guy is related to right convergence. So you might actually say, okay, so now I divide here by the number of vertices. I pull this, so I have a sum here. I pull the 1 over v, so, and then I interchange the limit and the sum, and the two of them are equal. And now you see that actually left and right convergence are equivalent, right? Because if these numbers converge, then we get this sum, and which is the same as these numbers converging. but I've cheated, okay, because I can't always, okay, so you have sort of in one direction, you have that right convergence. So what do we have here? This is left convergence. So left convergence would imply right convergence. And if I invert this relationship, so now I think of this as an infinite matrix, I multiply it over to the other side, then I can solve for these guys. And therefore, right convergence implies also left convergence. Well, but I cheated, and it turns out that the cheating can be made rigorous only in certain cases. For the experts among you, if you're in high temperature, then actually it is equivalent. So it turns out that left convergent is equivalent to high temperature right convergence. But since right convergence is stronger than high temperature right convergence does imply high temperature right convergence, which is equivalent to left convergence. So therefore, right convergence implies left convergence. Okay, so I mean, just it turns out if you have, so for the non-experts, whether these sums actually converge and you're allowed to interchange all these limits obviously depend how fast these objects are. So these objects may be bounded by something. We have bounded degree graphs, so there are not too many of these guys if you take logs and so on. But on the other end, you divide by this guy. So this guy is bounded in some way we can control. And the question is how many of these guys are there? And that has to do with, since there's this inclusion-exclusion, if, for example, these HOMs were just, well, I don't know, what are the backgrounds of various peoples? If you sort of know a lot of combinatorics and probability theory, then you know that inclusion-exclusion only gives you the first term if you have essential independence. And so if the graph H is very near to the complete graph, then it turns out that you have essential independence of all these colorings. And then these guys, only the small guys are sort of important, and they decay exponentially in the side of F, and then the sums are convergent. What I did is sort of legal. Anyhow, so in other words, if you have the right conditions on this graph H, then you get this equivalence, and otherwise you don't, and that gives sort of this. Okay, so now this guy was local, I discussed, this was global. This one sort of is, well, it implies left convergence, so clearly it sort of must have some local stuff in it. But it's not equivalent, so it can't be just local. So it actually sort of contains both local and global properties of your sequence. Okay, so that is part one. Now comes sort of what is sort of new in this paper, namely the notion of large deviation convergence. So I wonder, maybe it's time for questions for this first part. So any questions on this so far?
Could be a naive question, but if you've got like a sort of process model, you know, like the World Wide Web is made by If you've got a process model where you're making each, you're growing to infinity by adding sort of vertices and edges from the previous one, and it's still sparse. I mean, presumably they have some notion of equivalence. Or so because they're kind of pathological.
Yes.
Those
so for example, if I look at this example, you actually will have convergence in all three kinds. And so if you have a nice way of generating these graphs, so for example, you don't run into, so we saw that actually the problems with convergence of quotients not being equivalent had to do with this funny things, whether you were sort of bipartite or not. It looked very funny because that was, but if you have enough randomness, maybe that doesn't happen. Okay, and maybe if it's sort of this process, this will also make things nice in that respect. So yes, I would expect that for many of these graphs, they actually, all of them hold. Okay, and I actually will come up, this will be the second part, with a version that implies all three. So you actually, for your process models, would have to check whether this notion of large deviation convergence, we introduce holds. And if this is the case, you would know that then they all hold.
But in the majority of these process models,
You don't have bounded degree.
you don't have bounded degree.
That is true.
Unless you'd have to construct it in a very careful way, perhaps, or
Right.
you could probably organize it, but
Now, I mean, you can do statistical physics on models with unbounded degree, but then what is a high temperature region becomes more complicated. I mean, a lot of the techniques will become much more complicated. But I think that, I mean, first of all, the counterexamples all hold. So far we have only one direction. And this direction, I sort of would be hopeful that it still holds, because I would think that if you go to sufficiently high enough temperature, you can still do this kind of cluster expansions and maybe prove it. I mean, I haven't done the details, but I would have some hope. Because if you have right convergence, you don't have to use it for everything in these formulas. You only have to use it in the high temperature region, and then things may be nice. Good. So large deviation convergence. So we had this convergence of this quotients. Okay, so this was convergent of these sets, which you can just think of. So these are, right? They had weights for the vertices and weights for the edges. So we have sort of Q color classes, that is Q weights, and then we have Q squared possibilities for the two endpoints of the color of the edge. So this is, and since we divide it by n and the maximum degree is bounded by d, this is something which lies in 0d to the number q squared plus q. Now, what we want to do for large deviation convergence. So now let's choose this coloring uniformly at random, and now study the random variable, which is just these, right? So you have a big graph, you randomly color it with Q colors, and now you look at, okay, what weights do you get? What is the probability that a random vertex is red, green, blue? What's the probability that a random edge is sort of colored red, green, blue, red, or whatever, okay? And so you study, and FQ is roughly this, the random variable. And now, well, so we will call the sequence large deviation convergence if for all Q, these random variables obey a large deviation principle with some suitable weight function. Now, I don't assume most of you know what large deviations are, so I have to define it. Okay. The D is the maximum, it's a bound on it's a maximal degree, right? So we said we look at graphs of bounded degrees, so D is the maximal degree you see in your sequence. So, what does it mean to be large deviation? Well, informally, you just look at, you fix some finite graph F, finite weighted graph F. Okay, so this is some finite weighted graph F. Now you look at your random coloring and you look at the probability that that happens to be Z-but. Now, in all likelihood, it's not, okay, because you have exponentially many possible colorings, and who says that it will have exactly sort of 3% of the vertices green and 5% blue and whatever. So it probably is going to be exponentially suppressed. But the question is, how strongly is it suppressed? And if the coefficient here converges as n goes to infinity, then it's called, we say we have a large deviation principle. Now that's very informal, so let's make it a little less informal, right? So this is sort of, we have this weight function, so now. So informally, I now write it a little bit different, okay? Namely, I now say that, what do we have here? Why did that? I thought I was doing this differently. Oh yes, no, it's good. Okay, so informally, first I said it's equal, okay, so we have to do limits, okay? And actually, so let's say that we look at this probability here. Okay, now we have some random event, some event A, okay? So we have some set. We want to know the probability that it lies in there. So we actually then want to, this will probably be, so this is very unlikely, it's exponentially suppressed. We divide by this guy and take the log, so it's a negative number. So clearly here, the most likely of these guys will contribute, okay? Which would correspond to taking an infimum here. Okay, so that is sort of the next rough version. Well, it's still not quite correct. Okay, so actually what you want is you have to do lim sups and lim infs to do this right. Okay, so what do? We actually look at the lim inf and lim sup because we don't know the limit exists. And we take the lim inf in the largest open set contained in A, and we take the lim sup in the smallest closed set containing A. And this is just technical, but now for the probabilists, it's correct. Okay, and before it was just roughly correct. So now, for example, for these sequences of grids, or the torus where you wrap it around, you can actually prove that it's large deviation convergence. I mean, roughly speaking, right, I mean, these probabilities are just the flip side of saying the entropy, right? Because I have q to the n possible colorings. I say that this large deviation rate is sort of this e to the minus. Let me go back to the previous page. Here, right? So it's sort of suppressed like that. There are q to the n many colors, so q times e to the minus I is the entropy per vertex of your colorings when you fix sort of these cuts. And so you have to calculate these entropies. And if you want to do that on the grid, what you do is you say, I cut my grid into two pieces. And then I say, well, the number of edges which are red, blue, if I leave out the edges here, I don't make too large an error if n is large, because that's a vanishing fraction. And now I can do it independently here and here. So that means now these two entropies, so this number here and this number here factor. And if you take the log and divide by the size, then you have sort of half the size and half the size here. So roughly, except for this small correction here, you really dividing, sort of making your thing double as big doesn't really change that much. And for those who really sort of want the technical term, it's a simple subadditivity problem way to show.
So in large deviation theory, topology is often very important. And you see that here reflected in the A bar and A naught.
Right.
What kind of topology do you put on your space?
So here since I have just a finite subset of R, right, so I have R I have 0D to the q plus q squared, it doesn't really matter. We take the L infinity, but you could choose the L1 norm. It doesn't really matter.
There you see what might go wrong if you have unbounded degree.
Right. You would get, right, you have to think about the topology, and there are sort of certain equivalences which become sort of harder and things like that. For example, this, well, anyhow, it turns out that you can calculate this, rather than looking at sort of these general sets A, you can often look at sort of balls of certain radius with some epsilon around it. And already there you only get equivalent if you're in a compact space, otherwise you only have conclusions in one direction. And so life will get harder. It's definitely true. Okay, so now we have a theorem which says that if a sequence is large deviation convergent, then it's right convergent. Okay, and in fact, we can actually calculate what the free energy is. So assume that H is a soft core graph with Q vertices. Then I claim that the free energy is just the supremum over all these weighted graphs F of what? Well, here's the large deviation rate. Here's log Q minus the large deviation rate. So that's, as I discussed before, the entropy, right? This counts how many colorings are there if you fix the side of F. And this is sort of if you fix how many edges are red, blue, how many vertices are blue and red, and so on. There was actually, originally there was an N, right? Is there a tray? Oh, I see. I thought it was sticking. Good. So when we had this partition function, so this was e to the n times this free energy, okay? Oh, I should, let me call this f, which depends on your finite graph. So this was just equal, I mean, in the limit, so that's the sum over all colorings from V of G into V of F of the product over the A phi of X and the product over edges. What was this called? Beta phi of X, phi of Y. Okay. So what happens now is that if we fix sort of these quotients, then we know how many red, blue, how many green, and whatever edges there are. So we get sort of here, and we divide it by n. So we got e to the n times, so we now get over sort of ij, where this goes now over red and blue and so on. And now you get sort of the number of, let me just say, red, blue edges divided by n, right? And in a similar way, you get here e to the n times size of red divided by n, and then the product over all reds and blue and so on. So now you want to divide out this n, you get your, and then you have to count how many of these guys are, you get the entropy, and you recognize all these terms. So if I take out the n, then actually I get these ai, well, it's not e to the, it's ai to this, and this is beta ij of h. Okay, and these guys were just measured in the quotients. So these are these guys. Where's my color? Go on. Shut this thing off, yeah. Okay, so you see if I take out this n here, then I get just these quotients, and I have to take, and then I get an entropy, and now I have to take the maximum here. Why do I only take a maximum? Well, once I fix what the sizes of these cuts are, there are only polynomial many solutions. So if you take a log and divide by n, that sort of creates a supremum. So this is a very rough indication of the proof for people who sort of have done something like that before, and for everybody else, probably not useful. Anyhow, so you can actually, if you have large deviation convergence, calculate these free energies from this rate function. And so in the limiting free energy, the sequence Gn only appears via this guy, right? And the target graph H only appears via these weights. So it nicely factors sort of into these two contributions, sort of a nice energy entropy principle in which you get here. So what have we done now? So this is what we had before. We had said all these things not much implied anything. Okay, we just said that right convergence implied left convergence. And now we have this large deviation convergence, and I convinced you that large deviation convergence implies right convergence. Okay, that's sort of one of our main theorems here. And so what else do we have? Well, I claim now that it must imply this. Why? Well, large deviation includes right, which implies left. Okay. And why this? Well, that's not so hard, because large deviation convergence calculated what this rate is, or if you want, what the entropy is. Well, if you know the entropy, then we can just say a quotient will actually be, this was just the set of quotients which survives. This counts how many there are there. And if there's none there, then I can see that in this rate function, because then the entropy should sort of be 0 or minus infinity, or however you normalize it. The rate function should be. So it turns out that the set of quotients is just all these guys for which the large deviation rate is finite. Okay, because we divide, we have sort of, the number of possible guys could be at most q to the n. Okay, so if I divide by q to the n this rate function, if there's any contribution, it's at best suppressed by n. So if you divide by n, you get something finite. So therefore, in order to see which guys contribute, you just have to look whether the rate function is finite or not, and that's how you get this implication. And now the rest is sort of, this can't imply that. Why? Well, if it implied that, then this would imply this, and this would imply that, but we know it doesn't. And the rest can be filled out in a similar way. This can't imply that, because otherwise left convergence would imply large deviation convergent, which implies right convergent, but we know left convergent doesn't imply that. And finally, this can't imply, right convergent can't imply large deviation convergence, because if it did, then we would know that, let's see, if it is, then right convergence would imply convergence of quotients, but we know it doesn't. Okay, so we have filled in, so we know all these relationships. And so what is sort of the upshot of this? In the contrast to dense graphs, where all of these are equivalent, we hadn't shown that in our papers with Lazzi because we never introduced this notion, but you can actually, with some work, show that for dense sequences, this is also equivalent to the other three. So for dense graphs, all these different notions are really the same. Whereas for sparse graph, if you want to discuss convergence, you really should ask yourself, what do you want to know? And depending on that, you have to look with a different lens. And you may want to look at sort of the, maybe you want to do large deviation convergence because it implies all others. But maybe that's sort of too strict. Maybe for certain things you can't really expect that. For example, if you could prove large deviation convergence for random deregular graphs, you would get convergence, you would get right convergence there, and you would solve a lot of spin glass problems. Okay, so it's probably still true, but maybe there be too much to ask yourself to prove. And there may be certain cases where you really can't expect that. And then you should ask yourself, well, do you want to be an extremal combinatorialist? Then you may want to look at left convergence. Do you want to do sort of computer science? Then maybe the right notion of convergence is that of quotients. Do you want to do statistical physics? Then the right notion of convergent is the convergence of free energies. Yeah.
Okay, thank you very much, Christian. Are there any questions?
So do you have some interesting examples where you can show large deviation convergence?
Well, the grids.
The grids.
So as I said, it's sort of the first question you might ask about random deregular graphs, but we don't know. So there are a lot of interesting conjectures.
It's probably hard.
Yes.
Yeah. What do you need of your large deviation rate function? I mean, in many cases, you can identify the rate function as being 0, always. And then it's not very interesting.
I doubt it will be 0 always here.
I mean, there are examples where it will be. So you probably need some sort of convexity or strict convexity, or I mean, these are general settings in Lorentz deviation theory where you somehow demand properties of your rate function, and then you get all sorts of nice properties from the Lorentz deviation principle. For example, the formula you were writing looks a lot like Vardan's lemma.
Sure.
Yes.
And you need some properties of the rate function in order to be able to apply Vardan's lemma.
Right, so
You have it as a transform, basically, so it will have some of these properties, right? I mean, once you write the formula.
So I think what,
In that way.
so one of
Once
the,
you write the formula in that way with the energy and entropy, then you basically have it as a Laplace transform, essentially. So you have some of a Legendre transform, and then you have some of those properties, right? So.
well, it would be called equivalence of ensembles, right, in physics. I think one of the things which really helps here is that you work on this compact space, in which case you have this nice fact that you can express this large deviation rate in terms of balls of sort of, well, shells of width epsilon around sort of balls. And that's a bound, I mean, what he calls it, the n-sphere. And that actually allows you to sort of write these formulas. I mean, what I wrote here is that you can sort of say, okay, I fix this exponent up to plus minus epsilon, and now the large deviation rate can actually be written in terms of these, due to the fact that you have sort of compactness of the underlying metric space. So I think that what makes sort of the large deviation theory very nice here is exactly the compactness of the underlying space. So maybe that's the answer to your question.
Are there any other questions? Okay, so let's thank the speaker again.